Electromechanical differential relay have traditionally been used by electric power utilized to protect power transformer, and many of these relays are still in use in power system today. Differential protection with second harmonic restraint, which block the differential element during inrush event for the transformer in the basic protection of power transformer. One of the most dependable and real-like method of power system protection is differential protection. Transmission Company of Nigeria, which is TCN, use differential protection as the standard method of protecting transformer from short circuit. Since it is a selective method. Kirchhoff current law is used particularly in differential protection. The total current flowing into the transformer and the total current flowing out should be equal. It is determined that there is no fault in protection zone if the net sum of the current entering and leaving the zone is particularly zero. Okay, next, the problem statement is electromechanical relay will initially use of the transformer differential protection. Many these gadgets are still in use today, and digital relay are now an option. For this electromechanical relay to establish the fault location, internal or external, a set of current at each side of the transformer must go through physical summation. On the protection transformer, the inrush rating was set on a preface basis at 50% of second harmonic and 35% of first harmonic. The differential relay element set 0.4 inrush rating current was researched.
Now I would like to continue to the next part of this presentation, which is the transformer differential protection system modeling. So, without further ado, let's take a look to figure 1. Show a typical differential relay connection diagram. Power transformer differential relay inrush is commonly used and the most reliable technique in power system protection. Differential protection is a fast, selective method of protection against short circuit in transformer, and is the standard protection used by transmission company to protect the transformer. The Kirchhoff current law is put to use in differential protection, which is a practical application of the theory. The total of the current entering and exiting the transformer should match the sum of the current entering and exiting the transformer. If the net sum of current entering and exiting a protection zone is essentially zero, it is assumed that there is no fault in the protection zone. If the net sum is greater than zero, the differential protection concludes that a fault exists in the zone and takes steps to isolate it from the rest of the system. Differential protection creates a differential current by comparing the measured current entering and exiting the transformer. When current is flowing through the transformer with the ideal transformer, shown in figure 1, and assume ideal current transformer, the differential current is zero. An internal fault condition is indicated by differential current greater than zero. Due to measurement error and the position of the load that changes, the differential current for a normal operating transformer is always greater than zero. Misoperation can occur during transformer energization due to harmonic restraint function failure. An external fault can also cause a misoperation during the voltage recovery period, causing the differential relay to operate immediately after a fault is removed from the system. Percentage restraint differential protective relay have been in service for many years. Differential element compare an operating current with a restraint current. The operating current, also called differential current, can be obtained from the phasor sum of the current entering the protected element. So the next slide is discussed about the typical differential relay operating characteristic. This characteristic consists of straight line having a slope equal to an horizontal straight line defining the relay minimum pickup current. The relay operating region is located above the slope characteristic and the restraining region is below the slope characteristic. Differential relay perform well for external fault as long as the current transformer reproduces the primary current correctly. When one of the current transformers saturate or if both current transformers saturate at a different level, fast operating current appears in the differential relay and could cause relay misoperation. Some differential relay use the harmonic caused by current transformer saturation for added restraint and to avoid misoperation. In addition, the slope characteristic of the presented differential relay provide further security for external fault with current transformer saturation. A variable percentage or dual slope characteristic originally proposed by Sharp and Glassburn further increase relay security for heavy current transformer saturation. Show this characteristic as a dot line. Current transformer saturation is only one of the causes of false operating current in differential relay. In the case of power transformer application, other possible sources of error are the following: mismatch between the current transformer ratio and the power transformer ratio, variable ratio of the power transformer caused by a tap changer, third, phase shift between the power transformer primary and secondary current for delta Y connection, and the last, magnetizing inrush current created by transformer transition because of energization voltage recovery after the clearance of an external fault or the energization of a parallel transformer.
I would like to explain alternative transient program ATP software. It is software that we use in this journal. Aside from computing transient, ATP provides significant modeling capabilities and other crucial characteristics. Several non-simulation supporting options are available. Procedures that are useful for producing model data is provided in this software. Besides that, this software forecasts time-dependent variable and interest in electrical power network that are often brought on by some disturbance. The time domain differential equation of system components are solved using the trapezoidal rule of integration. Rotating device, transformer, surge protectors, transmission line, and cables are just a few of the various varieties that ATP software offers. Next, I would like to explain about the apparatus that has been used in this journal. The apparatus that has been used in this journal is power transformer. Power system often consists of numerous sites of generation, distribution, and linkage to other parts of the system or to other systems such as a nearby utility. Power transformer are chosen based on the application with a larger unit, placing more focus on unique design. Power transformer are available for step-up operation, also known as generator step-up (GSU) transformer, which are mostly utilized at the generator, and for step-down operation, which is largely used to feed distribution circuits. There are single-phase, three-phase power transformer available. The design of a transformer is determined by its intended use. Transformers made for indoor use are typically dry, though they are potential be submerged in liquid. Transformers are frequently submerged in liquid when they are used in outdoors. Next, I will explain about the protection system that has been used in this journal. The protection system that we use in this journal is differential relay protection system. The relay whose operation depends on the phase differences of two or more electrical quantities is known as the differential relay protection. Two currents come from two different areas of electrical power circuit and are combined in differential relay system circuit. It works in the principle of comparison between the phase angle and the magnitude of the same electrical quantities. There are some essential conditions required for the working of this differential relay protection. The network in which the relay used should have two or more similar electrical quantities. Second is the quantities have the phase displacement of approximately 180 degrees. The differential protection relay is used for the protection of the generator, transformer, feeder, latch motor, and bus bar.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fadli bin Azmi and I'm going to present my presentation about verify the proposed protection apparatus. Based on the article, it has proposed microprocessor-based differential relay protection as the protection apparatus. To verify the protection apparatus, basic laboratory experiment was carried out. This experiment was carried out to find the best option for the inrush restraint method and the inrush restraint mode. The Switzer Engineering Laboratories SEL487 microprocessor-based relay type was configured to some inrush restraint function and level setting method. The experiment procedure was to choose setting for the relay, connect the relay to the three-phase test set, simulate the system using alternative transient program ATP software to examine the level of the second harmonic present. These tests were repeated using different set point and different restraint function until a standard setting operating criteria was determined. standard package of setting was verified by recording transformer inrush data from numerous installations and comparing the set point level to actual second harmonic level to ensure there is enough margin. The experiment was set into the following criteria before setting and testing. A minimum level setting for harmonic restraint at 15%. No operating time delay for the differential element is introduced by the selected inrush restraint function or inrush restraint mode. The differential element is blocked from operating during this actual energization event. Furthermore, the relay's adaptable configuration logic was used to implement the inrush restraint mode. Star-connected current transformer, which is common in modern installation using diffusion relay with microprocessor, are used in this test procedure. As you can see, these are the figure of diffusion relay test procedure flowchart. For step 1, we must set relay mode. Step 2, set relay level. Step 3, play fault. When we play fault, the differential trip, we must reduce the level and repeat back the step 2. After the differential level did not trip, we must record mode level, and then the last step is change mode. These are the figure of the waveform of inrush current. The second figure is the second harmonic during energization characteristic. So based on the result obtained from the experiment, set point for the inrush restraint current or differential relay element was 15% of second harmonic, while the fifth harmonic was set at 35%. This setting were restraining the differential element when fault recovery magnetization inrush event occur. The setting also gave a good margin of security of energization of transformer. The operation of the differential element on any phase operates the circuit breaker supplying the transformer. The restraint criteria was met on all phases as the transformer do not trip during energization or sympathetic inrush. The magnetization inrush current generated during the transformer energization for this application was sufficient to activate the differential element. The result demonstrates that the differential relay operating current is zero since the total of the current entering its primary restraint winding equals to the sum of the current existing in its secondary restraint winding. This means that the protection zone is in perfect working order. Okay, these are the table for the relay differential setting, while the table 2 is the differential element relay setting for harmonic restraint result. So, there are few highlighted advantages of microprocessor-based differential relay protection. The first one is high stability against inrush current due to the advanced filter technology and optional cross-blocking function. High stability against over-excitation, which is on the fifth harmonic blocking. Short tripping time, typically 1.5 cycle. And lastly, high set of fast tripping, less than 1 cycle. That's all from me. Thank you.
For the discussion, the setting of inrush current due to harmonic in power transformer shows that 15% of second harmonic for the inrush restraint current in the differential relay element set point, and the fifth harmonic was set to 35%. This setting offer a suitable margin of safety for the transformer energization in situation when the second harmonic current may decrease to low level. When a fault recovery magnetizing in rush event occurred, the setting effectively restrained the differential element. In addition, the circuit breakers supporting the transformers are operated by the differential elements operation on any phase. It shows when the transformer does not trip during energization or sympathetic in rush, the restraint will be met at all phases. For this application, the transformer energization produce magnetizing in rush current sufficient to activate the differential element. As a result, the differential relay operating current 0 because the total current entering its primary restraint winding equal the total sum of the current leaving its secondary restraint winding. Differential protection generates a differential current by comparing the measured current entering and leaving the transformer. The differential current is 0 when current is flowing through the transformer with the ideal transformer, assuming ideal current transformer. A condition of internal fault is indicated by a differential current greater than 0 due to the CT measurement error and the positioning of the loop tap changer. The differential current for a normally operating transformer is always greater than 0. Result of microprocessor-based differential relay field configuration and harmonic restraint setting in the EMJ44803 shows that advantages that can get from the microprocessor-based differential relay protection, which are integral ratio and vector group adaptation, integral thermal overload protection, the external start of fault recording, and high stability against over-excitation at 5 harmonic blocking. Furthermore, high stability against CT saturation provided by the integrated saturation detector and add-on stabilization with the high stability against inrush current due to advanced filter technology and optional cross-blocking function also will be the advantages that can be collected from the harmonic restraint setting in the FEL 4X7. In conclusion, if there are very low second harmonic inrush level present, lowering the harmonic restraint setting will guarantee the transformer energization are successful. The setting is selective enough to identify between an inrush event and other event that may produce second harmonic current while being sensitive enough to detect magnetization inrush current even at low level of second harmonic. Although the transformer's energization produces high enough magnetization inrush current to activate the differential element, when energizing a faulty transformer's harmonic blocking or harmonic restraint element provide fast tripping for all internal transformer fault with the least amount of the delay. The purpose is to prevent the differential element operating during the transformer energization, transformer overexcitation, and voltage recovery following power system fault.